Hi, I'm Dr. Bill Miller III, and in today's mini lecture, we're going to be talking about chemical equilibrium. Equilibrium is the state in which both the concentration of products and the concentration of reactants does not change. So when I say this, I mean that the concentrations don't change, but that does not mean that reactions are not occurring, just that the concentrations, the level of the amount of stuff in solution does not change. So in general, to this point in general chemistry, you've seen reactions look like this. So for the decomposition of dinitrogen tetraoxide, which is in the gas phase, you see something like this, where it decomposes to 2 molecules of nitrogen dioxide. The problem is this isn't reality of what's going on. In reality, we see dinitrogen tetraoxide go in both a forward direction to 2 nitrogen dioxide molecules, but we also have present the reverse reaction, where 2 nitrogen dioxide molecules get together to form a dinitrogen tetraoxide molecule. So we see both the forward and reaction. And in chemical equilibrium, the rate of both the forward and the reverse reactions are exactly the same, and thus the concentrations don't change. So if we were to graph the reaction rate of this particular reaction, the decomposition of dinitrogen tetraoxide, as a function of time, at the very beginning, what's our reaction rates going to be in our forward and reverse reactions? Well, in reverse, since we have no product, the reverse reaction doesn't occur. So we know that at the very beginning, the rate of our reverse reaction is 0. But the rate of our forward reaction, since that's the only way it can go, is all the way as high as it can go. This rate will lower for the decomposition in the forward direction as a function of time until it reaches a solid value and doesn't change. The reverse reaction will do the opposite of that. It'll start out at 0, and then it'll slowly increase until it reaches the exact same rate as the forward reaction. So at this point, where they meet, we've reached chemical equilibrium, and that's where we are from there on as long as nothing else changes. So that's how the reaction rates occur. Now let's look at a plot of the concentrations in the forward and reverse, or of the 2 products and reactants. So if we plot this, we're going to look at the concentration in molarity as a function of time for both the reactants and the products. Well, at time 0, how much of the reactants do we have? That's all of it. All we have is reactants, so it's all the way up to the top. The products, at the very beginning, we're going to assume we have none. So it'll be all the way down to the bottom. So for the reactants for N2O4, we're going to see the concentration slowly decrease as N2O4 decomposes to NO2. So this is for N2O4. But for the product, NO2, we're going to see it start at 0 and it's going to slowly increase until it reaches a constant value. And this is NO2. Notice at this point the concentrations don't have to be the same. The reaction rates have to be the same, but the concentrations do not. And at this point, once the concentrations stop changing, once again, we're at chemical equilibrium for the rest of the reaction. And that's going in both the forward and reverse reactions. Now, we can quantify this ratio between N2O4 and NO2, and that's what we call the equilibrium constant. And it is abbreviated K with a subscript C, like that. And in general, the way we write the equation for the chemical reaction, or how we solve for it, is by doing the concentration of the products over the concentration of the reactants. For a general reaction, let's say involving two molecules, or two compounds, A and B, with subscripts little a and little b, they go to form two different molecules, C and D, with subscripts for their molar coefficients. If we're to calculate equilibrium constant for this general reaction, we're going to see products, which are C and D, and they're going to be raised to the powers of their molar coefficients. So little d and little c. And on the denominator, we're going to have the molar concentrations of the reactants. So we're going to have the concentration of A raised to the little subscript a, and then the concentration of B raised to the molar coefficient of B. Now for our example here, our decomposition of N2O4 to nitrogen dioxide, Kc is going to be equal to our product, which is NO2, squared, because there's a molar coefficient of 2 over it, in front of it, and then on our denominator we're going to have N2O4, and since the coefficient is 1, it's going to be only raised to the 1 power. Now chemical equilibrium at 25 degrees Celsius, this value is a constant because, like I said, the concentrations here don't change at equilibrium. So at equilibrium for this, the value is 4.64 times 10 to the negative third at 25 degrees Celsius. But what happens when we're not at equilibrium? When we're not at equilibrium, we can use something called the reaction quotient. And it is abbreviated with a Q subscript C. And it's calculated the exact same way, products over reactants. So for QC for our reaction, our decomposition of dinitrogen tetroxide, we have NO2 squared over N2O4. Now let's take for an example that we have, let's say for example we have our concentration of N2O4 not at equilibrium, so this is not at equilibrium. For a concentration of N2O4, let's say it is 0.2 molar, and for NO2, our concentration is 0.1 molar. If we calculate our quotient coefficient, QC is equal to 0.1 concentration of NO2 squared over 0.2, which is our concentration of our N2O4. If we calculate that, we get 0.05. And what can we do with that number? Well, we can relate QC back to our equilibrium constant. If QC happened to be equal to KC, to our equilibrium constant, then we know that we are at equilibrium. Okay? But if our quotient coefficient is less than Kc, then we know our reaction is going to proceed in the forward direction. In contrast, if our QC is greater than Kc, then we know the dominating reaction will be in the reverse direction. So for this example, since QC equals 0.05, which is greater than our value at equilibrium, which is 4.64 times 10 to the negative 3, that equals Kc. That means QC is greater than Kc. And that means that our reaction will occur in the reverse direction. So we'll end up seeing NO2 get together with to form dinitrogen tetroxide. And that today is your lecture on chemical equilibrium.